Hi everyone, welcome to our webinar. This webinar is a presentation of Clean Energy Group's Resilient Power Project in collaboration with the Northeast Electrochemical Energy Storage Cluster, also known as NESC. This webinar is part of our webinar series on hydrogen and fuel cells for resiliency, and the topic of this webinar is microgrids for grid power. Our host for this webinar is Todd Olinsky-Paul. Todd is a project director here at Clean Energy Group, and we also have two excellent guest speakers with us today. And before I pass it over to them, I'd like to go over a few quick housekeeping notes. All of our participants for this webinar are in listen-only mode. You have a couple of options to join the audio portion of this webinar. You can either connect using your computer, mic, and speakers, or you can call in using your telephone. A very important note, we ask that you please submit your questions at any time throughout the webinar as you think of them by typing them into the question box on your webinar console and hitting send. We will be reading through your questions as they come in. We'll be saving some time at the end of our presentations for an audience Q&A, so type your questions in when you think of them. Don't wait till the end to submit your questions. We will get to as many as we can. A final note, this webinar is being recorded. We will send you an email following the webinar with a copy of the webinar recording and a link to the slides. You'll also be able to find it within about 24 hours on our website, resilient-power.org, and you'll find all of our previous webinar recordings at that web address too. With that, I'd like to pass it over to our host for this webinar, Todd Olinsky-Paul.
Thanks very much, Samantha. Welcome everyone to the webinar. This is another in our series of fuel cell and hydrogen webinars within our Resilient Power Project series. And I'm going to do a brief introduction of who we are and what we do, and then I'm going to introduce our speakers, and we'll get right into the webinar. So Clean Energy Group is a nonprofit. We have been doing this Resilient Power Project for a couple of years now, basically several years now, since Sandy hit the Northeast very hard, and we started getting calls from state energy offices wanting to know what they could do to assure power supply to critical facilities in case of this kind of natural disaster or other grid outages. And so we've been doing this work for a while. We work with states, municipalities, developers, other NGOs, industry groups, and we're supported in this by a number of foundations who have been very generously supporting our work. You can see them on the screen here. If you'd advance the slide, please, Samantha. So just a bit more on what we do. You can see here a bullet list of some of the goals of the project. We have a specific focus on protecting low-income and vulnerable communities. These are communities that are typically hit harder in outages and in natural disasters, and don't typically have as many resources to cope with these sorts of disasters and power outages as other communities do. So we've been focusing quite a bit on that. You can see at the bottom of the slide there are some case studies that we've produced that are available on our website, and also we've produced quite a number of other webinars that are also archived on our website. So in addition to this webinar, I encourage anyone who's interested in the topic to go to our website and look through our resource library. This is sort of basically a screenshot. You could see at the top there our web address where you would go to look for those resources. Next slide, please. And so I want to also do a brief introduction for NESC, the Northeast Electrochemical Energy Storage Cluster, which funds this webinar series and with which we are partnering for this series. NESC is a network of industry, academic, government, and non-governmental leaders working together to help businesses provide energy storage solutions. And specifically, niche focuses on hydrogen fuel cells. Next slide, please. So I would like to go ahead and introduce today's guest speakers. I want to remind everybody that we will be taking questions throughout the webinar. You can type them into the question console on your screen, and please do that as they occur to you. Don't wait until the end, because I will be sorting through those, compiling them, and getting ready to present them to our speakers for today for answers and discussion. So if you could send them in as soon as you think of them, that would help, and it will make it more likely that your questions will be addressed. So our speakers for today, in order, well, they're going to bounce back and forth a bit, but the first voice you will hear will be Robert Rose. He is Vice President of Specialty Services with AZ Corporation. He has 30 years of industry experience, including design, large and small scale plant operations, and facility maintenance experience. He also has expertise in electrical utilities, high voltage, power distribution, instrumentation, controls, and microgrid development. He is a licensed professional engineer and master electrician in Rhode Island, Massachusetts, and Connecticut, and he holds a BE in electrical engineering from SUNY Maritime. He is also active in the Institute of Electrical and Electronics Engineers, or IEEE, and the International Society of Automation, or ISA. He's joined today by Ben Tobey, Vice President of Sales for Fuel Cell Energy of Danbury, Connecticut, where he works with colleges, hospitals, utilities, municipalities, and industrial clients. Ben has 25 years of experience in the distributed energy industry. Prior to joining Fuel Cell Energy, he was responsible for international sales for FCE. He was Vice President of OEM sales for Capstone Turbine Corp., and he was a combustion engineer with GE Energy and Environmental Research. He holds an MS and BS degrees in engineering from the University of California and is an individual member of the Association of Energy Engineers and a certified energy manager. So, with the introductions out of the way, I'm going to go ahead and turn this over to our speakers, Ben Tobey and Robert Rose.
So welcome, everyone. Thank you for the introductions. We wanted to start our presentation by just taking maybe a half a step back from the specific area we're going to address today, and just talk about kind of the definition of a microgrid. And we took this from the state of Connecticut DEEP requirements because the state of Connecticut is fairly well developed in implementation of microgrids in various capacities. So it's interconnected loads, it's distributed generation. There's a lot of different versions of that. Today we're going to focus on fuel cells. It also is defined electrical boundaries. Today we're going to talk about utility interconnects, but a lot of the work we're currently doing is on it's behind the meter. And then control of these different sources of generation. On the next slide, so one of the things that we often find when we're working with utilities and/or private clients is the goals of the microgrid need to be defined on the front end. Analysis of existing infrastructure needs to be understood and the different ramifications. Financial options, financial considerations. Microgrids can have very pronounced societal benefits or commercial benefits to different clients, but microgrids do have a cost to them. There are various funding vehicles, but there is a cost typically for resiliency. And then the technical requirements tend to focus primarily on the interconnect and subsequent distribution. In the grid-connected applications, the thermal distribution tends to be a smaller aspect based on those applications that we've completed, and then a reliable fuel source. Some areas we have coincident electrical and gas distribution. Other areas, those two systems don't intersect as well, which creates a further challenge.
Good afternoon, everybody. It's Ben Toby with Fuel Cell Energy. Have a quick slide here to describe the advantages of fuel cells really quick. Many of you may be familiar with this. We make rather large fuel cells. Our smallest unit is a 1.4 megawatt fuel cell producing approximately 11,000 megawatt hours of electricity per year. These units have some good advantages in the sense that, first and foremost, they are able to deliver energy cost savings. We're active in the Northeast and on the West Coast of the United States as well as internationally. And in those markets where power prices tend to be on the high side and there is value placed on environmental considerations, we can certainly deliver energy cost savings for our customers. We're here today to talk primarily about reliability and grid-independent operations. As well, the fuel cells are very clean. They produce virtually zero criteria air pollutants and typically do make a substantial contribution to the reduction of greenhouse gas emissions from the atmosphere. They are fuel flexible. Our systems basically will operate on any methane-containing gaseous fuel, be it natural gas or anaerobic digester gas, etc. And they also find themselves very easy to permit generally because they are so clean. They really fly through permitting processes. So this is arising as a result of the fact that the fuel cell is an electrochemical device. We're not burning any fuel. We're converting it from chemical state into electricity and heat by way of electrochemistry. So that's why you really don't get the emissions that you would with a combustion process and really paves the way for so many of those advantages. I have two slides to just provide a high-level overview of the two fuel cell systems that we manufacture. These systems are manufactured in Torrington, Connecticut. They are 1.4 megawatts in size and 2.8 megawatts in size. I won't go through the details of this slide, only to suffice to say that the space requirement you can see on the bottom right of this slide is around 40 feet by 60 feet in size. There's a little bit of flexibility. We can move a little of these parts around and so forth, but generally speaking, you need a size around the size of a tennis court, 40 feet by 60 feet. You can see in the box there to the right, the pollutant emissions are really negligible, and you'll find them at least an order of magnitude lower than equivalent combustion-based systems. Output from our 1.4 megawatt system is 480 volts, and as I say, 1400 kW. The output voltage can be varied based on different transformers and so forth. Finally here, the LHV electrical efficiency is 47%. Which is really, really superior in comparison to many equivalently sized combustion-based technologies. Additional efficiency advantages are definitely available by harnessing and use of the exhaust heat that is exiting from the back end of the plant. Similarly, with our larger system, the 2.8 megawatt system, pretty much the specs are identical. The output is twice the size, and the footprint, I apologize that you have to squint just a little bit. The footprint is approximately 60 by 90 with a slightly larger area needed for replacement of fuel cell stacks at 5-year intervals. So the shaded area in the bird's eye view really is intended to signify where you roll the crane up and get those stack modules replaced every 5 years. Apart from that activity, the requirement is about 60 feet by 90 feet on the facility site. Showing here a picture in real life of what this fuel cell installation looks like. This particular unit is located at California State University East Bay in Hayward, California, and is a 1.4 megawatt DFC 1500 fuel cell. To the right, of course, you can see the 1.4 megawatt stack module. That is the box containing the fuel cells themselves and is producing 1.4 megawatts worth of DC electricity. The DC exits out the top of the box and goes down that little ramp and wires through the inverter. Our inverters are manufactured by Rockwell in Wisconsin. The job of the inverter, of course, is to convert the DC power into grid-referenced AC, in this case at 480 volts. You see some switchgear that is for the purpose of interconnecting the electricity with the, in this case, PG&E electric grid, as well as the campus. In the back of the photo, you see heat recovery unit. That's a fairly typical size and shape for a hot water heat recovery unit. That unit is manufactured by Kane Industries, also here in the U.S. And then finally, we have a shipping container that contains water treatment system and some other skid-mounted equipment for the purpose of creating steam and reforming natural gas into hydrogen before it enters the fuel cell. So these are the high-level component layout of our system, and you kind of gives you a feel for what it looks like. Just a quick note on the cost. The cost of electricity with our systems is in the range of 12 cents per kilowatt hour. The key input here is the fuel cost. This 12 cents per kilowatt hour has three primary components to it. One is the capital cost of the plant itself, fully constructed. Secondly, the fuel cost that is required to run the plant. And then finally, the maintenance of the plant over typically a 15 or a 20-year period. If you take those three major components of cost and add them together, a typical number is in the range of 12 cents per kilowatt hour, assuming $4.50, pardon me, $4.50 per million BTU natural gas cost entering into that equation. So, you know, there's many parts of the country for which this will not be competitive, but I think on the coast and certainly in our experience in the Northeast, that can be very competitive. Finally, on the cost, any value that can be accrued from renewable energy credits, the federal investment tax credit, and the usage of exhaust heat will subtract from that 12 cent per kilowatt hour number and arrive at something that's typically in the range of 9 cents or thereabouts per kilowatt hour. Okay, transitioning a little bit now to a technical discussion. The fuel cell is capable of grid-independent operation. The primary design is for what we refer to as grid-connected mode. In this mode, we have a connection to the grid, we've got a connection to the facility, and the facility is really blind to whether it's getting electrons from the fuel cell or from the grid. So in our normal operation, if someone has a base load requirement of 1.4 megawatts, we're just offsetting the purchase of grid power at that facility, but they don't really know whether those electrons, frankly, are coming from the grid or from the fuel cell. It's just a grid-connected operation. The second mode that we've been able to introduce is what we refer to as a microgrid mode. In this mode, we employ what we call a load leveler, so that the power that is generated by the fuel cell that is not required by the facility when the grid is not present is consumed in the load leveler. Naturally, you want to minimize that consumption in the load leveler, but it does allow us to serve transient loads on the facility side because our fuel cell is a base load resource. It really runs flat out 24/7. So naturally, what we would do in the sense of a grid interruption, in this case in our microgrid mode, is we're running the fuel cell, we're matching what the facility needs, and if on a steady state basis, absent the grid, you are below the rated output of the fuel cell, we will gradually ramp down the fuel cell so that we're not wasting fuel. And then finally, we have our critical supply mode. The critical supply mode takes power hardwired from what we call our customer critical bus, and it hardwires that power into critical loads on the customer side. In that sense, the breaker that connects the customer critical bus over to the customer critical load is not subject to interruption or opening in the case of a grid outage. So we can continue to flow power from our customer critical bus when the grid goes away, whereas in microgrid mode, we're connecting through our tiebreaker that does need to open, so you see a temporary interruption of power in that mode. So to summarize then, the microgrid mode, we refer to it as a drop and pickup scheme. You see about a 1-minute interruption in power flowing from the fuel cell to the facility. In the critical supply mode, there is no interruption, and it is a seamless provision of power to the customer's load. Okay, so I have 3 brief slides to address each one of those. I've substantially described them already. I gather that these slides are available to you should you want to look at them offline afterwards. But grid-connected mode, just quickly here, you can see inside the dotted lines and kind of to the top of the box there is a tie breaker. That's the breaker that's opening when the grid is experiencing a difficulty or an outage. And this, of course, is in accordance with UL 1741 and IEEE requirements. We have to disconnect from the grid to avoid energizing and backfeeding a dead grid. On the next slide, we're going to show our microgrid mode, and that shows the tiebreaker there is going to open, and we will provide power to the customer's loads after a brief interruption in the drop and pickup scheme, as I mentioned. Very often, we will equip this configuration with a small gas or diesel genset that allows for the fuel cell to black start in the event that the fuel cell is down for maintenance when the grid goes away. A highly unlikely eventuality, but occasionally, just to get that extra security of secure power, we will employ a small genset to black start that fuel cell plant. And then the next slide, and finally again, is this critical supply mode. In that sense, you can see kind of where the blue box is. We tie the critical loads into our critical bus, sort of within or upstream from the tiebreaker that's subject to opening in the grid outage. So you'll see how the power can flow regardless of whether the grid is open or shut. We have case study examples for each 3 of these modes coming up in just a moment. One quick note for you electrical engineers who may be on the call, because we are inverter-based power technology, we are capable of power factor correction from 0.9 to 1.1 power factor there. And the chart is showing our kVAR generation capability as a function of real output on the fuel cell. So in many locations where you may be at the end of a distribution line or be subject to dirty power and so forth, this can be a valuable asset of inverter-based power generation like a fuel cell. Okay, the first case study we wanted to talk about is the University of Bridgeport in Connecticut. That's a medium-sized university, maybe small, depending on your point of view, but they have about 4,000 students, Bridgeport, Connecticut. Really interesting project here in the sense that this is primarily, from our point of view, a fuel cell combined heat and power project for which the economics which drive the fuel cell installation are based on energy cost savings and full utilization of thermal energy from the fuel cell. In the upper left corner, you can see the fuel cell installation. The building directly adjacent to that is a fitness center with an Olympic-sized swimming pool. So they use about half of the heat that we produce to heat the hot water for that swimming pool. To the upper left corner is a university-owned apartment complex, which similarly takes some of the exhaust heat from the fuel cell, uses it for domestic hot water purposes, and out of the photo they do have a dormitory which does the same thing. So we were able to pull in 3 different sources of thermal load, which really provides a strong engine for the economics on this project. Very important to the university as well was to deploy this fuel cell as the generation source in their microgrid. You can see the picture in the bottom there. The red lines show their electric wires essentially on the campus, and the green boxes are showing the facilities that are connected to the fuel cell driven microgrid on the campus. And Robert's going to speak to this in just a moment. I think I hit on the advantages. In a university setting, it was very, very important to them that we engage the university community. They have a very strong engineering program at University of Bridgeport, and they really wanted us to create an opportunity for the students to learn about cutting-edge energy technology, which we most certainly do.
So the University of Bridgeport project was a recipient of a grant from DEEP, and that grant will allow the university to automate the on-site medium voltage 13.8 kV distribution loop. So on the campus, There's approximately 9 G&W switches. All of the switches are being removed and replaced with motor-operated switches. We're installing an SEL microgrid controller, and this will allow the campus to automatically open and close loads and manage the load to the output of the fuel cell if they are in an island mode. We've been working with UI, United Illuminating, that's the local utility, and this project will go into final testing this summer, and the university should be in a much better position for power interruptions and weather events, which the university happens to be right on the water, so they have experienced outages in the past.
Our next example of the three, the second of the three, is a microgrid project that we are currently building with United Illuminating and a school district in, the town of Woodbridge in Connecticut. Amity Regional District 15 is the host at their high school there. So AZ is going to be building this for us. They're in process now. The picture kind of on the bottom is a rendering of the fuel cell in the back of the high school, what it will look like when it's done being constructed. This is a very unique project in the sense that the customer, as I said, is United Illuminating. During normal blue sky operation, when there is no grid problem, all of the power from this, in this case 2.2 megawatt fuel cell, is being exported to the United Illuminating grid. They are permitted to own this generating asset by a special law that was passed a couple of years ago in Connecticut, which allows the utilities in our state to own up to 10 megawatts of Class 1 renewable power. So a relatively modest number, but nonetheless, UI elected to use part of that allocation to do this project. It is providing power out to the grid in normal operation for grid support, and it is providing hot water to the high school by way of a heat exchanger that we're installing so that the high school can see a reduction in their utility bills. So that's very beneficial. The other aspect of this is that for the microgrid side of things, UI applied for and received, the town of Woodbridge applied for and received Connecticut deep funding to install a microgrid that is going to keep the town energized. On the next slide, Robert will walk us through how that lays out, but the fuel cell here provides power in a grid outage to not only the high school, which serves as a point of refuge for the community, but also about just under a mile away, the town hall, the fire station, the library, etc., via dedicated underground wires that are being put in by UI expressly for this purpose. So we're working with UI's engineers to really get this microgrid design ready to go, and it's going to be constructed this summer and into the fall. And I think I hit on the advantages there.
So the topic of today's webinar was microgrids for grid power, and this project I think most closely resembles that that topic. The challenges with microgrids is funding. The challenges with microgrids is finding coincident thermal and electric loads. And in this case, the DEEP program helped support it. And the town and cooperation with the high school. So on this project, we're through permitting. We're about to break ground. The interface is UI is installing some new switchgear at the school that will facilitate the microgrid. The microgrid will have dedicated cabling and automatic controls so that the town or that UI can regulate the load on the microgrid. So we want to have distributed generation. We want to have microgrids for grid power, but ultimately, their biggest value is when they're in a microgrid mode. The challenges quickly become segregating the load that's most important, and then managing the load to the generation. The fuel cells with the load levelers may be one of the best qualified methods to do that, because load swings in a microgrid will become very challenging. So again, this one is getting closer to our topic, getting closer to what the end game is, I think, so that all this distributed generation can have a, let's say, a positive or a more measurable impact when we're in storms or other utility interruptions.
The third and final case study that we wanted to call out is at the Pfizer R&D Center in Groton, Connecticut. This is a unique privately owned microgrid. This project will encompass 2 of our 2.8 megawatt fuel cells for a total of 5.6. The power will be connected to our customer critical buses, to the Pfizer critical loads, such that when the grid goes away, power keeps flowing. This facility does a lot of very important R&D research for the Pfizer company, and when they see both quality swings on the grid and out-and-out outages, which is occurrence with some, not regularity, but it happens, they experience an awful lot of cost and other pain. So that really was the driver for them to approach us and say, hey, let's do a microgrid. Having said that, the project does deliver very substantial savings as well in comparison to what they would otherwise be paying for their grid power. The heat is harvested and converted into steam. In this case, 45 psi steam that they can route directly into their header, which is used for campus steam needs. So again, it's a deployment of the fuel cell in a really sort of the application and technical fit of this project is fantastic, and it drives really substantial savings and reliability benefits to Pfizer.
So this project is also under construction right now. Concrete has been placed and equipment will start being set in the near future. Pfizer, like many industrials or colleges, universities, has its own distribution loop. They distribute power at 13.8. In this case, the fuel cell will run base load in parallel with a 10 megawatt gas turbine, and this project interconnects to Groton Utilities, so it's a municipal. The load at Pfizer, while it peaks above 15 megawatts, could certainly be arranged to configure this site in an export as an export if circumstances required. But as Ben said, Pfizer's primary motivation was their science. Their science can't tolerate power interruptions or power quality issues, and this project has the critical bus, which can also be of vital importance to different people. So we've touched on the 3 different configurations of microgrids here. We'll roll into Q&A shortly. A couple of other projects that we didn't feature as case studies, all 3 were in UI territories, but 2 of them were 2.8 megawatt fuel cells on a distributed basis for grid support. They haven't been completely configured for microgrid operation, but could be put into a microgrid with manual switching by UI. And then the largest project in Connecticut is the Bridgeport fuel cell, which is 15 megawatts that just generates power, and again is in a position to export power through manual switching of UI.
So in summary, I hope we conveyed the advantages of fuel cells for microgrids. This is proven technology. Fuel cells have been around a long time. We, as Fuel Cell Energy, currently have just over 200 megawatts of our systems deployed domestically and overseas. The costs have come down in a pretty substantial manner. We're still not to the level of reciprocating technology from a cost vantage point, but in those locations that value environmental attributes and for whom folks have to pay a lot for power, we can really bring in some good savings. I guess I would conclude by saying that these fuel cell microgrid projects are complex projects in the sense that you need an economic engine to drive the installation of the core generating asset, and then the reliability benefit that the microgrid investment brings can be kind of an add-on. And again, that's kind of my perspective, but we generally develop the fuel cell project as an energy cost savings and a sustainability benefit project, and then we bolt on, in some sense, the reliability benefit associated with converting the operation of that fuel cell to microgrid mode. So many thanks for your attention on the webinar, and we're happy now to answer questions.
Great, and thanks very much to both of you. That was very informative. We do have a large number of questions queued up, and fortunately we've got some time to address them. So hopefully we can get through these, and if anybody has a question that they are just formulating, please feel free to go ahead and send it in, and we'll get to as many as we can. So the first question is directed to Ben. The question is, how important are incentives to fuel cell adoption? How will the industry be affected by pending changes to incentives, including California's SGIP, which is the Self-Generation Incentive Program, and the Federal Investment Tax Credit?
Yeah, it's a very, very good question, and certainly there will be an impact. I want to first emphasize that the 12 cents per kilowatt hour that I communicated on one of the prior slides is without any incentives. And additionally, the benefit of heat recovery in most of our sites, if you get to full utilization of heat recovery, its equivalent worth is about a penny and a half. So you're at 10.5 cents per kilowatt hour. Having said that, there's a fairly limited amount of customers at our size level, that is to say, that consume that much power, who are paying, in that range. They do exist, and when we find them, we're very happy. But most of the country is served by power that is below that. So that really gets to the question. In the near term, I think we've got some challenges relative to the extension of the investment tax credit and the SGIP program in California. But I think over the longer term, there is both a reduction in cost of fuel cell that is going to continue, and I think a continued acknowledgement of the advantage of this kind of technology on a societal level, which will give rise to new incentives. A less generic answer would say the investment tax credit, we feel really good about it being extended. Just very much this week, we've seen some very nice public statements by the leadership in the Senate to that effect. In California, there is a strong need for storage that we are competing with, but I see generation, especially ultra-clean generation, playing a role going forward side by side with storage in California. So thanks for that, and it's very on point.
Great, thanks. Next question, can the fuel cells be powered by renewable fuels?
They most certainly can. Our fuel cell is designed to operate on methane-based fuels, so anaerobic digester gas that would arise from a wastewater plant, a food and beverage operation, this kind of thing, organic digestion, can be used to power the fuel cell. Anything down to about 50% methane, with the balance being whether it's CO2 or nitrogen is fine, can be used very, very well in our fuel cell. And I've got probably about 20% of those 200 megawatts I cited earlier, 15-20% of those are operating on biogas fuel, on renewable fuel.
Great, thank you. Somebody wants to know, when do you have to decide if you want to be in grid, microgrid, or critical supply mode? And are all the modes available at the same time and have intelligent controls to sense when each is necessary?
So decisions about implementation are best to weigh out the costs and the benefits fairly early on. Creating a critical bus does create additional cost. So I'm going to say it's not something you want to change after the fact. You can have critical and non-critical loads. However, this is an early-on decision, is what I would just say. It's an early-on decision, and be prepared to stick with your decision. The cost impact will be substantial if you want to change it later.
Right. I think what the questioner was trying to ask, I may be just interpreting this from my own point of view, but it sounded to me like the questioner wanted to know, does the microgrid essentially automatically island in case of an outage, and does it automatically go to critical load support at various times due to however it's configured? And I'm assuming the answer is yes. Those are automated modes that come on when they're called for.
So it's a qualified yes. So yes, all of those things can be accommodated. In the case of the University of Bridgeport, we're in the process of automating everything. If you do set up a critical bus, then that's inherent to the system design from the get-go and wouldn't require any additional automation. So it gets down to load segregation during the initial phases, and it's important for everyone, let's say the host facility, fuel cell energy, and any member utilities to understand, what the goals are on the front end, because there are hardware and associated cost impacts.
Great. Okay. Somebody else wants to know, during grid outage operation, how are load transients being dealt with?
So at the University of Bridgeport, we worked, and we're still working with fuel cell energy to understand the block loading that the fuel cell can handle. So they've developed a model, and honestly, a big portion of the model in the case of the University of Bridgeport pertain to the transformer, the inrush current on the transformers. So we built a model. We put switching in, and we put load management in so that we won't overload the fuel cell. And then the fuel cell has the load leveler on it. So between those different components, we believe we have a system that's fully automated, and that's what we're going to test late July to prove everything out. So we believe with a load leveler and the SCL microgrid controller, this is a fully automated system that'll deal with inrushes and equipment starting and stopping.
Great. Well, thank you. That leads us to another question from somebody who wants to know what a load leveler is. Is it just a load to allow constant output, like a variable resistor, or are you doing something useful with the power?
It's the former. The load leveler is simply a PLC-controlled resistive load bank. So that's where I was kind of aiming at with my comment earlier about you don't want to run this way for an extended period of time. We would tune the output of the fuel cell during the grid outage to try to match, as close as you can to minimizing, wasted fuel. So it is a resistive load bank. But on the positive side of things, it allows you to continually get that reliable supply of power during a grid outage and accommodate the transients that exist with the loads that you're serving.
Okay, thank you. Somebody wanted to know what this DEEP funding is, and I can answer that. It's Connecticut Department of Energy and Environmental Protection, and they had announced a $40 million microgrids grant program. They've now gone through 2 rounds of competitive solicitations where they funded a number of systems, and they're currently offering their remaining funding in a rolling submissions format where rather than have a deadline for the competitive bids to be submitted, you can submit proposals whenever you are ready, and they will continue to accept them until the money is dispersed. And they have, I don't know exactly, I think there are maybe 3 or 4 functioning microgrids now that were funded under that program or partially funded under that program, and a lot more that are under development. So just to catch people up on what DEEP refers to. Next question. The person says, I understand fuel cells do not ramp up and down very readily. Is that true? If true, is a fuel cell useful for providing ancillary services to the grid like spinning reserve or ramping?
Yeah, that is true. Our fuel cell is a molten carbonate fuel cell, and it really doesn't like to ramp up and down. So we generally are we're providing base load, be it to our site host in a behind-the-meter application or to the grid itself in a grid support application. As far as other types of fuel cells, my understanding is that high-temperature fuel cells that deliver high efficiency, like ours, are generally not as good with the cycling. I know ours certainly isn't. The lower temperature fuel cells, like PEM fuel cells, for example, are very well suited for cycling, and that kind of a fuel cell is being deployed in residential type applications and also vehicular applications where cycling is really important. From the standpoint of ancillary services, I'm not an expert on that area, but I can say that we participate in capacity auctions very often where we are able to monetize the capacity benefits of the fuel cell. I'm not as much aware of the spinning reserve and I guess the word was load following attributes. I don't know, Robert, if you have any background on that. Generally, the economic value of our projects derives from selling the electrons, selling RECs, or otherwise monetizing the environmental attributes of the fuel cell and capacity. I'd love to look into the others, but I think to your point, it may be a little challenging or of a stretch for us given that we are base load technology.
Okay. Did Robert want to chime in on that, or should I go?
Oh, no, I nothing to add to that. I think the basis of the load leveler, the addition of that by fuel cell does allow the fuel cell to respond to variable loads, whether it's behind the meter or to the grid. Now, there's certainly a range in that, but I think the load leveler largely addressed that variable load requirement, which is inevitable when you're in a microgrid orientation.
Okay, great. Somebody wants to know whether the Woodbridge microgrid would have been feasible without the dedicated underground wires, and if not, are most municipal microgrid facilities more closely located? Is there a rule of thumb?
Yeah, my view is that it could have been done with above ground wires, but certainly the system will be more robust and less likely to experience difficulties when it is operating in microgrid mode with underground wires. That was the decision that UI came to. I think it's a really good decision. Of course, it drives additional costs. But having said that, there's nothing saying that you can't use above ground wires for implementation of a microgrid. You might have to be ready for a little bit less reliability in the case of a tree falling on a wire or something like that.
Right. I think it may have been a requirement of the DEEP grant program. There were a number of requirements that applied to different types of technologies. So, for example, if you were going to use on-site fuel, you had to have, fuel tanks that were resilient and not, had to have a certain amount of resiliency built in. I think undergrounding the wires was part of that. And the idea was, we want a resilient microgrid that's going to continuously supply power to critical facilities during a natural disaster. So, going through all the expense of setting up a microgrid and then having, wires on poles that are going to be knocked down doesn't make a lot of sense. So I think that was probably the origin of that. And probably should say that there's different kinds of microgrids. There's this sort of municipal or type that we were talking about here, where you have a number of different facilities that are connected, and then there's the sort of campus style that we've also discussed, where you might have everything behind a single meter, very closely connected on a campus, and you may have different kinds of requirements. I know right now, for example, in Massachusetts, there's a proposed microgrid that's received some state funding in Northampton, where they're trying to connect a hospital, a school, and a Department of Public Works facility. And so they have these 3 facilities behind 3 separate meters with 3 different owners. And in that case, it's a little more, the business model is a little more complicated. And you have to get permission to, for example, run electricity across the street, which you have to get a waiver from the utility right of way to do that. So there are different requirements and different layouts for these things. Okay, I'm just going to move on to the next question, which has to do with data centers. The question is, do you have any data center case studies, or if not, what would you project for typical cost savings in dollars or percentages, i.e. in place of battery, UPS, boiler, chiller, etc.?
I'll say, yeah, sure. I'll say to that we are just rolling out next year a product that we feel will be very well suited to large data centers. It's a 3.7 megawatt fuel cell plant which runs at 60% electrical efficiency. So in that sense, the heat output is, if you will, kind of an afterthought, and the main driver is the very high electrical efficiency. That product, again, is a 3.7 megawatt fuel cell, so it should be very well suited to large data centers. As far as a percentage reduction, I pretty much know the percentage reductions we normally deliver to our on-site power CHP projects is around in the range of 20, anywhere from like 15 to 30% savings as compared to what they pay to the utility grid. I don't, unfortunately, have the answer to your question, which is the percent savings as compared to, a battery or other type of data center solution. That is something that's kind of in the works right now, and I don't have it for you.
Okay, and who was that speaking?
Ben Toby.
Thanks. So, yeah, just it'd be helpful if you identify yourself for those listening. Okay. Next question, how do ITC tax credits or lack thereof play into the circumstances of the case studies?
Ben Toby speaking. Okay. The ITC was deployed on all 3 of those projects. So the University of Bridgeport, Town of Woodbridge, and the Pfizer project. Now, the Town of Woodbridge was an equipment sale, an EPC contract between Fuel Cell Energy and United Illuminating. So United Illuminating would have been the ones to be in the position to monetize the investment tax credit. So I'm fairly sure that they were able to do that, but frankly, it's because they are the owner of the plant, they're in the position to either do that or not do that. And I'm not 100%, but I feel fairly certain that they did monetize the investment tax credit. The model on the University of Bridgeport was a power purchase agreement that we signed with the university. We subsequently brought financing by way of NRG Yield, and NRG Yield is monetizing the investment tax credit on that project. Similarly, in the Pfizer project, Pfizer, we are monetizing the investment tax credit under the PPA in a similar manner that we did at UB. With our third-party investor that we're bringing in that's going to own the fuel cell plant at Pfizer. And I would say, I guess, perhaps the thrust of the question, I always kind of come back to cents per kilowatt hour benefit associated with these things. It varies a little bit because some of the taxes are a little bit complicated, but generally speaking, the investment tax credit is worth about $0.015 per kilowatt hour. So it has a substantial impact to the project.
Right. Are there any, I mean, it's just to follow on this, are there any requirements that are placed on fuel cells in terms of how they operate in order to be able to take the ITC? And I'm asking that because I know, for example, if you look at batteries, there are some caveats. In order to take the ITC, they have to be charged from renewable sources, for example.
Is there a
Is
minimum
there anything similar for a fuel cell?
From the standpoint of the investment tax credit, there are not. Fuel cells are categorically qualify for the 30% investment tax credit. You're right on the money with regards to some of the state incentive programs. For example, New Jersey requires the overall efficiency of a fuel cell installation to be in the range of 62 to 65% overall efficiency. You know, in order to qualify for an incentive that New Jersey makes available. California has its requirements, Connecticut and other states have their requirements. The investment tax credit, if you are a fuel cell, you are qualifying for the ITC.
Great, thank you. So here's a money question. What is the average cost per megawatt hour? And that's a big question.
Per megawatt hour, it's going to be, per kilowatt hour is 12 cents, so per megawatt hour is $120, is that right? Yeah, $120 per megawatt hour.
Okay. Let's see. The next question is regarding the cost breakdown for typical fuel cell installation and operation. What are you considering operational costs, as they seem like a large part of the total project cost?
Sure. Fuel cell maintenance and fuel, the fuel provided to the system, are typically what I consider to be operating costs. There is a little bit of water that flows to the system, but it's pretty trivial, frankly, in terms of the cost. And that is about the sum of those two between the maintenance and the fuel is probably about 2/3 of the project. And the remaining 1/3 is the plant itself and the financing for that. Maybe it's a 60-40 breakdown, something in that ballpark.
Okay, thank you. Somebody wants to know whether you have any experience with integrating renewables such as PV with fuel cells, and are there any special concerns regarding reliability in doing that?
We do, and I can point to a project in California where we have a fuel cell installed at Santa Rita Jail, which is a prison in Alameda County, California. Now, they have deployed megawatt-class solar PV array in parallel with the fuel cell and also energy storage. We did not handle the engineering of that integration, but it is very, very well coordinated, and the fuel cell operates very nicely in parallel with the renewables there. It's also very common for us to operate in parallel with conventional technologies, gas turbines and gas recips. At the Central Connecticut State University, we operate in parallel with 2 megawatts of gensets in serving a microgrid at that university. And in Southern California, at the University of California, San Diego, we run in parallel with a 30-megawatt gas turbine installation with one of our 2.8 megawatt fuel cells. So as long as the kind of companion generator is large enough to provide a reference signal that is good and strong, and usually it's like 1.5x or 1x to 1.5x as a minimum in terms of the size, we can use that parallel generation source as, if you will, a surrogate grid with which to operate and generate our signals and make good, clean power.
Okay, and I'm assuming that, given what you said about ramping earlier, that you're not, you're not load following essentially with the fuel cell. So if you have a fuel cell and something like PV, which is highly intermittent, or can be, do you then have a third component, such as either a battery or some kind of fast ramping device that can reciprocating engine that can follow the intermittency and make sure everything is kind of kept to kept to the desired level of frequency?
Yes. So either those two that you said, or the load level that we talked about earlier can serve that function. So I'll say that the battery or the gas recip or gas turbine would be sort of additive load following, which is to say they just follow the loads themselves and cycle up and down accordingly. The load leveler is kind of like subtractive load following. We're running base load, at a higher than they need, and we're burning some of that excess energy so that we can serve the load transients. But in any one of those three cases, you're just fine with providing power output to the loads.
Okay. Well, look, we've reached the end of our hour. I'm sorry that we did not get to all the questions. We had a whole bunch of them, and we got to as many as we could. I want to thank today's guest speakers, Robert Rose and Ben Toby. And do we have any upcoming webinars, Samantha, that you'd like to mention?
Sorry, I was muted. We have a bunch coming up. You can find info about them on our website at cleanegroup.org/webinars.
Okay, very good. Well, thanks again to our speakers, and thanks to everybody who attended. Again, if you want to review the webinar or send a link to somebody who wasn't able to attend, it was recorded or is being recorded and will be archived on our website. And feel free to review it and all our other webinars. See you next time. Thanks for attending.